CrossFit. And so I didn't get a day off. Huh? Why do you get suckered into CrossFit?
That takes some effort. That or Grace is really gullible. One of the two. Why can I not get this in a spot where there's not a ton of glare?
How's your day, Dr. Joe?
My day is fantastic. It is Friday, so that's always positive. That's always positive. We're recording all this stuff too, so that's always good.
Did you clear your disk?
You know what was going on? I knew it was recording and saving it in one spot, so I was keeping that cleared out. Now it was saving it in two places, and it filled up an entire other part of the hard drive that I didn't know it was filling up. So, yeah, I got rid of it now. It's all good. So, I deleted all those files. Suddenly I have 200 gigabytes free. So, it's very interesting.
I wonder how it saved to two places.
I have no idea why it saved to two different places, but it did.
So
Lucky me. What do you want? What are you saying, Grace?
That I want to work day.
She wants to go live.
Apparently she wants to go do CrossFit. You want to work on problems? Is that, you want to see some problems? Is that what you're telling me?
Preferably the homework problem. So
Well, how about if I do ones that are like the homework problems that you have to do, or at least examples? Deal? So you're saying you want to do nothing new today? Okay.
Let's learn new stuff.
Really? I think that's the first time you've ever taken it.
That's what I was going to do anyway.
Great minds think alike.
Next week we're going to start doing annuities. So next week we're going to be looking at the videos again.
How many videos is this? Are you teaching those videos?
I teach. The videos go for chapters 6 through 11. I'm doing 9 through 11.
Wait, so we're flipping it 6 through 11?
The videos are 6 through 11. Yes. I know. Yes, you should be very. I should be very telling you why.
It took 3 people from this class last night to tutor somebody in intermediate on compound interest.
Yeah, it did.
By night.
Yeah, we got stumped.
It did. We were like, we didn't know it. It didn't tell us if it was compounded or simple, and we couldn't figure it out.
It took us 3 people to figure out a simple interest.
But we got it. It turns out it's compounded, but annually. So like N is 1.
Gotcha.
Also,
That sounds
if you're talking
great.
about
Sounds
making
great.
a monthly payment, it's compounded monthly.
Oh yeah.
It didn't say that in the problem. I was like, oh.
The formulas that they have to use if they're doing regular payments, the formulas have to match payment period and interest period.
Okay, well, good to know.
Yeah.
After we got past that, though, it was smooth sailing.
After I left.
It'll be the same.
I knew it was an answer, and Sam was like, no, it's this. And I'm like, all right, fine, I'm trusting you. And then he was wrong.
Oh, well, there you go. All right. Let's see if we can look at one of these problems on the, I think it's the packet that I handed out last. Where is Marshall?
Hey, he's still got time. It's only
He's got -6 minutes. You know, it's fine.
It's only
I think I handed out last time. It says pass exam questions on sections 1B to 1F. That's
Oh
what
yeah,
it
we
says.
should do problems on those. All right, what can we do? Can I ask a question about problems?
How about I do it?
Okay.
Let's do a
Can we
problem
do-
number 8.
I want to do problem number 6.
How about 8, 15, 26, and 31?
How about I do number 6?
I'm trying.
I know you're trying. All right, so this problem, you've got $100 that is deposited into, what? Oh, you might want. What? Thought you were messing with me again, Grace.
Not that. Safe assumption?
Yeah, it's a pretty safe assumption. I did turn it on. Oh, and I don't have it switched over to the laptop. That's why it's not coming on. There it is. Hey, look at that. All right, so in this problem, you got $100 deposited into X and Y. X has a force of interest accumulation. So it says delta sub t is 0.5 times 1 plus t to the negative 2. And y accumulates value with an annual effective interest rate of I. And again, if the pardon me, if the problems tell you it's an annual effective interest rate, it's telling you that it is compound interest and not simple. And they also tell you that at 9 years, X and Y have the same amount in them. Oh, hey. It's close enough. And the problem asks you to find I. So, in general, as a review, how do we find accumulated value with annual effective interest? What would we do? Apparently we would do something quietly. Good. All right, so we know that our accumulation factor for annual effective interest is just 1 plus I to the t, right? Don't need to worry about the ends here at all because I've been compounding one time per year. Multiply that by the present value. That's how we get accumulated value at time t. In this particular problem, what do we know? We know PV and we know the t, right? For the fund y, right? So we know that at time y, at time 9, we know that we've got, for fund y, you would have your accumulated value at 9 would be 100 times 1 plus I to the 9th, right? Oh, it's in the 9th, yeah. I keep writing things that don't look like what they're supposed to, so. All right, that's stuff that we did before force of interest, right? That's not new-ish stuff, right? All right, so what do we do with the force of interest then? For in general, if we went for a force of interest, what are we laughing about now?
I set my notebook down in my fish wrapper.
Oh, no. How do we do accumulated value if we're using force of interest?
I like the PERT formula.
That looks like the PERT formula, yeah.
Except the R's.
It's the thing.
It's the thing I agree with.
E to the right. E times E to the right.
So our accumulated value is your present value times e to the. You gotta be a little careful.
What's that thing called again?
The integral? The delta?
Yeah.
Oh, okay. Yeah, but we have to do an integral in this case, right? Why do we have to use an integral? What's true about the force of interest in this case? Is it constant or does it vary? It varies, right? So remember, it's from time 1, well, if I'm doing from present value to accumulated value, it'll be time 0 to time t of delta of, I don't want to use the same letter for my variable for integration as I do up here in my exponent, so I'll say delta of s ds. It's bad form, remember, to use the same variable for what you have for your integrating, as far as what's up in your upper limit of integration.
Do you know that it varies because there's like a t in it?
Yeah. Yeah, and we know it varies because we have that t in the formula for the fourth dimension in this case.
Can I make an offer?
7. That was an odd request.
Instead of S's, can we use like
Was it?
instead of S's, can we use B's because they look like fives?
You may use a B. What if I have a U?
Great. Just
Uh-oh.
use whatever letter you want.
You can use whatever letter you want. We're gonna plug in. I'm gonna change it back to a T here in a minute,
Okay.
because we actually have a number to plug in up here.
I'll figure it.
You're good.
It's the wrong letter. It's for your work on exam.
Because that matters in that case. All right. So for this one, what do we know? For fund X, what do we know?
T equals 9.
Okay. We know that the T is 9.
PV equals 100.
Okay. The PV is 100. The T is 9.
DS equals 0.5 times 1 plus T to the negative 2.
Okay. And that's why I said I'm just going to change it back to a T anyway, because I'm going to make the number up there at 9. The only reason why I wrote this as an S and this is a T is because it's bad form. We had the same variable in both places. Because one's telling you what to integrate with respect to, the other one's telling you what to plug into the upper limit of integration. But since I don't have that problem in my second formula, I decided to go ahead and change it back to a T because Grace doesn't like S.
My questions?
I know what you're saying. Especially with my handwriting, you really can't tell the difference between an S and a 5. Well, Grace wasn't gonna say anything.
I mean, you said it.
All right. Now this one looks like something that we can do. We have all the pieces of information on this right-hand side, don't we? So we're going to attack this problem now. We're probably going to evaluate this and then do what? After we evaluate this, what are we going to do? What do they tell you? What else do they tell you about the funds?
They equal.
That they're equal at time 9, right? So we can evaluate this, plug that in up here, and solve for I, right? Yeah, so this one's not too bad. This one's fairly straightforward. So let's do the integral first. Integral from 0 to 9. 1 plus t to the squared dt. I need an antiderivative.
U equals 1 plus T.
Okay, your u would be 1 plus t, your du would be dt, so you're just integrating u to the minus 2, right? Antiderivative for u to the minus 2 would be
Negative 1.
negative 1 over u, so this is going to be negative 0.5 over 1 plus t, evaluated from 0 to 9. Everybody's looking at the integral strangely. Just a power rule, right? It's u to the negative 2. So the antiderivative would be negative u to the negative 1. No, there's no trig substitution. Nothing fancy here, right?
Not
That
I
what?
always gotta rewrite it like 0.5 times the 1 plus t. I
You
think
can.
it's definitely.
Well, that's how they actually wrote it in the problem. I just wrote it this way. You do what you have to do to get the problem done correctly. All right, so this one, when we plug in 0, we'll get 0.5. When we plug in 9, we will get 0.05. So we'll get 0.45, if I did that right. I know, I plugged them in backwards with it, because that's because there's a negative sign in front. It feels like I plugged them in backwards, right? But remember what happens when you have a negative in front? You can flip your limits. So if I put in 0, I get just 0.5. When I put in 9, I get a 10 on bottom, which gives me 0.05. And I subtract, I should get 0.45. Yes, you know.
Because it's negative 0.5 over 1 plus t, so that's 0.5 over 10. And then
That's 0.05.
Yeah.
And it'll be negative.
Yeah, over 10, right?
So yeah, 0.5 divided by 10 is 0.05.
And
Right.
then you subtract or you add
0.5
over.
over 1.
Oh, I thought.
Yeah.
I did the wrong limit.
Ah, gotcha. That okay? All right. This was our exponent in E, right? So we said that we can put this in now up there for the fund Y. So we would have 100 e to the 0.45 is equal to, oops, 100 times 1 plus I to the 9th. We agree? Divide out your hundreds. I need to get the I by itself, so what do I need to do to both sides? 1/9 power.
I got it.
When you do the 1/9 power, that's going to change this to 0.05, right? So if I solve this, you should get I is equal to e to the 0.05 minus 1.
And then 5.1.
5.12%?
Well, it's 1.3, but it rounds it to 1, so it's 5.1.
Okay.
So do actual force of interest have formulas like that, or are they more complicated than like the real world? Like if I go to a place, a bank, they're like, oh, your force of interest is 1 plus 1 over square root of x squared plus 1 to the dx. That's your force of interest.
Well, in the real world, they're going to be more complicated just because they change constantly and probably not according to a function. So you probably have to do some approximation anyway. Questions on this one? Are we okay with this one?
Yeah, I'm just checking something.
What are you checking?
It's on, oh, it probably just rounded it. Never mind.
Oh, here.
My calculator rounded it, so it was like a nice number. And
So you did it on the BA2?
yeah.
Okay, so,
It was only at 2 decimal places.
oh, the 2 decimal places, it would just stop, yeah. So if you do it on here, you would do the 0.05 and then do your E, so it'd be the second log there, and then subtract the 1.
Yeah,
Yeah.
I only had it at 2 decimal places, so it says 0.05.
Oh, yeah, gotcha. That's why I like to have it at 4. But some people put it at 8, but I think 8 gets obnoxious because so many of the problems when you start typing things in there, they don't have 8 decimal places in them. So I usually leave it at 4. 4 gives me enough to make me happy and not obnoxious.
We do 19.
19.
What is this random e variable?
Well, let's see what it says. Are we okay with this one? With the A?
Yeah.
Okay. Yeah. Yes.
How do you like put your calculator back in the order of operations?
Yep, I'll show you. All right, so go into second format. That's where you can also change your decimals. Okay. Use your down arrow. Mine is in order of operations mode. Yours is probably in chain mode, CHN. Do second set, and it'll flip it to the other one. Yeah. You're welcome. And then again, I'll just hit second quit. A clear might have worked, but second quit definitely does. Okay, so that A is talking about your accumulation factor. So your A of t is the accumulation factor at time t. So it's asking for it's asking you for the inverse of that function in 19. So all this means is that, remember for that first part in the previous problem, we had this. This part is your A of t. It's your accumulating factor, and you multiply by the present value. That's what the A of t is. So for force of interest, for the second part, if I'm doing present value, it starts at 0. Then just this part is your accumulating factor. Accumulation factor. So in some of the review manuals and some of the text, you'll see a little a of t and a capital A of t. Little a of t is the accumulation factor. Your capital A of t is your actual accumulation function. Then you multiply your accumulation factor by the present value. So the only difference between the two is accumulation function has the present value stuck out front. Pardon me, goodness. The idea behind with your force of interest, you'll notice that if I take the derivative, I know, I said a dirty word, didn't I? Take the derivative of my accumulation function in this case, accumulation factor, sorry. Well, this says do the derivative of e to a power. When you do derivative of e to a power, you get what? E to that power. And then times the derivative of the power. Right? What is the derivative of the power in this case? Well, we're doing the derivative of an integral. Yeah, so it becomes a function with the t plugged in, right? So notice on the left-hand side here, I took the derivative of the accumulation factor. The accumulation factor came back in again, right? So we can actually notice that the force of interest, this is another way to define your force of interest. It's the derivative of the accumulation function divided by the accumulation function in this case. And close off that parenthesis. So now it's an alternative way to define your force of interest. Not that it's necessarily going to come off, but it might. You'll see different things with derivatives occasionally. You'll notice that this works with a constant force of interest. And I'll go back to 19 in a second. But you'll notice that this works with a constant force of interest. If your accumulation function is 1 plus I to the t, then if you remember your differentiation rules, derivative of, we know that e to a power, its derivative is itself, right? But if you change the base, what do you have to do with the derivative when you take it? So instead of e to the t, if you had a to the t, what's the derivative going to be? Yeah, it's going to be a log a along with it, right? So the derivative here is 1 plus I to the t times natural log of 1 plus I. Notice what happens when you divide those out in this formula. What do you get for your force of interest? If I use this formula here for the force of interest and I divide these two, what are you left with? This is ln of 1 plus I. Isn't that one of the formulas we already had? One of our conversion formulas, right? No, I haven't done the problem yet. I was just showing some different pieces. You asked what A of t was, so I wanted to talk about a little bit more about the A of t. Yeah,
So is the prime symbol in the formula for delta t at the top wrong then because the derivative of
oh, yeah, that should be a prime there. Thank you. Go away. You're right. I wrote the derivative and then I wrote a prime. I confused the two. Or conflated the two. Sorry about that. You're right. The prime shouldn't have been there. Either that or the DD shouldn't be there. One of the two. Yes, it's a tick mark. Absolutely. All right. At any rate, this force of interest formula works nicely for for constant force of interest. Remember, we got to the constant force of interest by doing the limit of the compounding pieces. You can also get at it this way, doing calculus this way, which kind of makes sense because how do you define a derivative? It's a limit of something, isn't it? It's a similar fashion. All right, so let's talking about 19 then, now that I've gone through all of that mess. So the force of interest at time t is that, what is it, t cubed over 100? Is that what it says? It's a little small without my glasses. Yeah, t cubed over 100. Oops, not a. So your delta of t is t cubed over 100. So if I want my accumulation function, or factor, sorry, at that time, how do I find that? For accumulation factor, you don't worry about present value. You just worry about the accumulating part. So what is that going to be? So e to the integral from 0 to t of your, I'll say s cubed over 100 ds, or a v if you're Grace.
I'm using an S just for you.
So now I need to do antiderivative here. Antiderivative for s cubed over 100 is going to be what? Oh, you went the wrong way. You multiply by 4 instead of divided. Be 400. Evaluated from 0 to t. So you should just get e to the t to the 4th over 400. E does, but it's still on the exponent. I'm only plugging it up here. So it's only going to get a 0 there. You're right, e to the 0 is 1, but I'm only plugging it on the top. All right, so now we want the inverse of this. Basically, they just want you to do an algebra problem. Remember how you do inverses? Yeah, switch your variables and then solve for the variable, right? So if I think of this as my y and this is my, say, x, I would flip x and y and then solve for y again. So I'll write this, instead of flipping x and y, I'll flip t and y. So I'll write it as t equals e to the y to the 4th over 400. So what do I need to do now? Take a natural log of both sides. Very goofy problem. Multiply by 400. And then I got to take the 4th root. Which I have to be careful of because t can't be less than 1 if I take the 4th root because I make a negative natural log. Right? If I have a log between 0 and take the log of anything between 0 and 1, it's negative. Because 1 is where it crosses the x-axis, or t-axis in this case. And then I'd also have plus or minuses, but in this case, our function value can never be negative, so when I do the 4th root, I should use the positive 4th root. So this would be your inverse function. I don't even know why they're asking this problem. Apparently when they decided to use this problem, they were going to test your algebra skills. It's the best thing I can do for this. Not sure why they're asking this. Oops, that's not of 3, that's of t. So then you would want to put 3 in. So if I put log of 3 and multiply by 400 and raise it to the 1/4 power, I don't get what they... It's not going to be close. That's weird. Why is that not right? Well, I can't just be asking for the reciprocal because that's way too stupid. The inverse of the accumulation factor at 3. I put in 3, I get something.
I get 4.58.
Yeah, it doesn't make any sense. Unless I really do just. I can't want that. Well, it is entirely possible they really mean the reciprocal, because if I do the reciprocal of the function, I get 0.82.
What do you mean?
If I put in 3 here, and then take the reciprocal of it, and not the inverse function, but the reciprocal of it, I get 0.82. Meaning I put in 3 here for t, get a number, and then flip it upside down. I do get 0.8, I get 0.8167. So it's entirely possible they mean the reciprocal and not the inverse, which is not what that's not what that notation means. So what I would suggest doing with this problem is crossing off your sheet. Because that doesn't make any sense. That's not even the notation that you use for reciprocal. If you're going to do reciprocal, you should have a of t all raised to the negative 1. That symbol means inverse function, not reciprocal. So it's either a typo. Well, here you can't see.
That must have been a fun one to explain.
That's weird. I don't know why.
Past exam question.
This is a past exam question too. I know.
Scary.
Well, I mean, I guess you would know to try the reciprocal instead of the inverse if the inverse wasn't on there.
Since when is that a notation?
Or just skip it. What's that?
What is that a notation for?
It's not. It's the notation for the inverse. If I want reciprocal, I would raise the whole thing to the negative 1.
So how did you know to take the reciprocal?
Because the inverse wasn't giving me the right answer.
So you said, is it really reciprocal? And then you tried it.
And then I said, well, do they really do mean the reciprocal? And I tried. That's exactly right. I just tried it.
So maybe they just put the negative 1 in the wrong spot.
But that's a really bad spot to put it because that means a completely different thing. Yeah.
I'm a little lost with the, at the final answer, when we have n of t, is t the same as the t of the inverse function?
Yes, it would be. You would plug into that t. Yes.
It's still time.
It would be that t. We usually think of. Usually when you're doing this for x's and y's, you think of x as input and y as the output, right?
I would have replaced the t that the function.
So when you solve for your inverse functions, the trick to do is just to flip the variables and solve for the other. So that you can figure out what the input is into your inverse function. Of course, the whole idea with doing inverse functions is if I compose the two, I should get back to t, right? If I plug this in here, the 4th root and the 4th power will cancel out, the 400s will cancel out, and the e and the log will cancel out. So I really do get back to t. So that trick of flipping the x's and the y's is to just try to get the composition part to work out. So really, even though it says t in both of them, the domains have changed, right? In the first one, you plug in a t. That t is referring to time. You get out an a of t. That value is an accumulation. For the inverse function, even though it says t, what you're really plugging in is an accumulation and what you get out at the time. It's standard to leave your inputs and your outputs the same variable names, even if they mean different things in context.
Can we get number 28? Because I think it's asking what I think it does, but there was a problem it didn't, so
28. 28 is just asking you to do derivatives, right? So in 28, it says take the derivative with respect to v of the force of interest, multiply it by the derivative with respect to I of the discount, and then simplify. The answers are on the next page. So we can do this. What's that?
We thought there was more to the problem.
Oh, no, that's it. This is what I always do. I just want you to simplify it. So the way that I would attack this problem is that I would use our conversion formulas that we know to get the delta and the d in terms of the v and the I, respectively, so that I can take the derivatives. Okay. So for the first one, what do we know that delta is equal to?
Natural plus I.
Okay, natural log of 1 plus I. And then how is v defined? What is v equal to? It's 1 over 1 plus I. So what can I plug in here to get this in terms of v? If v is 1 over 1 plus I, what's 1 plus I equal to? 1 over v, right? Or v to the negative 1. And then what can I do with that exponent? Bring it out in front, so I get negative natural log of v. And that, like I said, that's literally just using our conversion formulas. And that's what this is an exercise in. And some of the problems on exam FM will pop up like this, where it's wanting you to understand what the formulas are and how to manipulate them. Those types of problems will pop up on exam FM. All right, so for the other one then, how is D defined in terms of I? Good. Because D is 1 minus V. So, and V was 1 over 1 plus I. So D is 1 minus 1 plus I. You could also write it as I over 1 plus I. That also works. If I get a common denominator there, I would get I over 1 plus I. Okay? All right, well now I've got both of these formulas where I want them, so I want to take the derivative with respect to V of negative log V, and I want to multiply that by the derivative with respect to I, and I wrote a T, of course I did, of 1 minus, and I'm going to write it as 1 plus I to the negative 1. Just because it makes it a little easier to differentiate. What's the derivative of log V with respect to V? It's 1 over V, so I'll get negative 1 over V times you're going. I just need to think derivative. You're thinking integral. You're not done about natural log. Derivative of 1 is 0. Okay. I'll start it off. So what's the derivative of the next piece? What do you put the power? Bring it out in front, so it's going to get a positive 1 plus I to the negative 2, and the derivative of the inside is 1. Got some mad differentiation skills going on here. So this is 1 plus I to the negative 2.
We did it.
Well, almost. We haven't matched the answers yet. The answers are on the next page.
I thought we did it.
Okay.
All right, so now we need to match the answers. What are the answers in terms of? All of them in terms of V? Yeah, okay. So I probably don't want to change the 1 over V. I probably want to change the 1 plus I to the negative 2. What did you say V was equal to again? 1 over 1 plus I. So 1 plus I to the negative 2 would be V squared. Good. That was much faster than the derivative.
I got it.
So you get negative V.
Hey, we did it.
Now we did it.
That's the answer.
Okay. Let's do one more. Let's see.
Oh my God, that's so fast.
It does go back pretty quickly, doesn't it? It's kind of fun.
It's because I never have any idea what I'm doing.
Let's see. That's a good one here to do.
9.
Let's do 22. Oops. I'm going to cross that out. 22. You know that your delta sub t is 2 over 1 plus t. A payment of 300 at the end of 3 years and 600 at the end of 6 years has the same present value of a payment of 200 at the end of 2 years and x at the end of 5 years. Find x. I don't know why I drew such a long line, but that's all right. I'm going to draw 2 different lines here. All right, so we've got a payment at the end of 300 at the end of 3 years, 600 at the end of 6 years, and that's supposed to have the same present value of a 200 payment at time 2 and an x payment at time 5. The reason I drew 2 different timelines is because we're supposed to be setting a couple of things equal, otherwise we're all on the same time diagram. All right, what are supposed to, with respect to these payments, what are supposed to be equal? The present values, right? So I need to move these back to time 0, right? Okay. How are we going to move it backward with this force of interest? We know accumulated value is present value and then e to the 0 to t of delta of s ds, right? That moves it forward. What do we do to move it backward? Yeah, we just do the negative of it, right? The negative exponent. Just like when we do anything else, when we're solving for present value, if we're given accumulated value, it's divided over, essentially, right? So, what's going to be the present value, then, of this $300 payment? How are we going to find it? Well, I just want to know what the present value of the $300 one is. Zero to 3 of the function is what again? 2 over 1 plus t? Is that right? Okay. That's the present value for the 300. It also has that present value of the 600 that's attached to it, right? This is a payment of 300 in 3 years and a payment of 600 in the 6 years. So I want to add the 600 e to the negative integral from 0 to 6, 2 over 1 plus t. This is your first time value diagram, right? This takes your 300, moves it back to time 0, and your 600 and moves it back to time 0. What should that equal? Okay, so tell me what it is. $200. Good. I must have forgot my dt over there, didn't I? Good. So on the right-hand side of this equation, we have moving 200 back 2 years and x back 5 years. Great.
How do you know when to add or to multiply? Like, in other problems, we're moving forward, we need to multiply them instead of.
Well, I'm still multiplying here, right? I have to take it, I'm multiplying by that discount factor. I'm taking the accumulated value and multiplying by the discount factor.
Yeah.
I've got two separate payments, so I have present values for both of them and adding together. So the adding is going through the fact that I need to take this 300 and the 600 and put it together
For present values.
So we multiply when there's different rates, that's when we do that, right? Like, when we had like a.
When you had a
Like 2% from 0 to 3, and then it moved to like 5.
Right.
6.
because you had to take it, move it forward until that new rate took effect, and then took that value and multiply it again. That was because we had to do that one individual payment and moved it in steps. Here we've got two different payments and drawing it back at one step. That's the difference between the two. Is that what you were asking, Greg?
Yeah.
Or we suppose we're what you were asking? Thanks, Sid. That's exactly right. Okay. So now it's just a matter of doing the computations, right? We just need to figure out the numbers to solve for x. We agree?
Yeah.
Okay. This antiderivative is going to be what?
2.
Yeah, 1 plus t. And that'll be evaluated from, and all of them are evaluated. I'm just going to do a general formula so I can just plug it in all at once. Okay. All of them are evaluated at 0. The top number changes, so I'm just going to write an A here.
Is it negative?
There's a negative in front. Yeah, I wasn't worried about the negative. I was going to take care of it in a minute, but that's okay. All right. So we plug in the 0, we'll get 0, won't we? Because log of 1 is 0. So this just becomes negative 2 natural log of 1 plus whatever that A is. So I can bring the negative 2 up. Now why did I do this generally as opposed, I'm almost out of time here. Why did I do this generally instead of doing each one individually? And what are we also doing with this? It's in the exponent with the E, right? I know, the E and the log are going to cancel, right? We agree? Yeah. Okay? So then all I need to do is just plug in these top numbers for all of these. So we're going to get, when we do the E and the log, they're going to go away. So this first one's going to be 300 times 4 to the negative 2. 1 plus the 3, right? Because the A was the upper limit of the integration. Plus 600 times 7 to the negative 2. Has to equal 200 times 3 to the negative 2 plus x times 6 to the negative 2. And then you should be able to go through and get what x has to be. I think Sydney's typing it in. I got 316.
Got
350. I got 315.82. Yeah. Okay. Okay. Cool. All right. So for Monday, you need to watch the videos for Chapter 6. More homework? If you want me to work on problems on Monday, I need you to watch the videos.
I know, you're killing me.
All right, have a good one, everybody. If anybody sees Marshall, tell him to watch the videos.
Okay.